Very good afternoon to one and all present here in online class. I am Dr. Sanjay V. I am currently working as a training officer in University in Chennai. Today, I am going to give a talk on the basic process that is iron carbon equilibrium diagram and its three important reactions. So now we can able to see this like have you heard about the word in the heat treatment? When you heard about heat treatment, that is iron carbon diagram is the heart of the heat treatment process because it has various properties. If you want to example, I will let me know with the example. We want a particular material with a hardness of say 30 hardness value, and some cases the hardness value is exceeded the material than the range of the hardness. Then what we can do? Either we have to use it. If you're using, definitely it may leads to failure. Or another one is we have to just throw it like a scrap. But heat treatment concept can able to regain the properties. So for that cases, this iron curve diagram is much useful. So I'm going to give that talk with that. So iron carbon system. This is a iron metal as well as carbon metal. These iron and carbon both are combined together and heating at the melting point. So this alloys of iron carbon system are most important to many industries which is having a very good applications. This include mostly steels and cast irons. So iron carbon diagram is used for steels and cast irons, not for any other metals. So this is also we can call it as it's a ferroalloy based iron carbon system. And in that iron, the carbon content is added, that is alloying element is added. Now, how much percentage carbon is added with the iron? So carbon is 2%. If we add, then we will call these as steels. And if we add more than 2% to the maximum of 6.67%, then that is called as cast iron. Now, why we need to go for carbon mixing to the iron? Why can't be iron itself? That will be the question many people can able to get raising it. The thing is, iron, pure iron is basically a weak material. Engineering materials talk about this material is not that much enough having the properties like say tensile strength or a hardness or impact strength likewise. At the same time, carbon is added to the iron, then it gives a very tremendous increase in properties and applications. That is why we are going with this concept. Now, here, family, you have to know about each and every metal's melting point. So, do you know about the iron melting point? That melting point is 1539 degrees Celsius. So, you can see here at 1539 degrees Celsius, iron is in liquid state. That means when we are heated the material, that is iron material, above the 1539 degrees Celsius, it is completely liquid. Now, when we are maintaining certain time to the liquid state, now entire solid phases makes into a liquid state. Now we have to stop the furnace. So automatically, gradually, slowly, it will be decreasing the temperature. When decreasing temperature, the solidification may start growing. There are important properties will be leading it up. So here, the cooling curve of pure iron is a very important one. Afterwards, I will go back to iron carbon equilibrium diagram. When iron solidifies, that is, when melting point below it touches, it will be in the form of del form. There are three symbols we are going to see it. Del form, that is delta ferrite, and This is basically has a body-centered cubic structure. I hope you heard the word body-centered cubic. So, okay, I will just show the structures. When you see here, this is body-centered cubic. Just a minute. Yeah. When we move to this body-centered cubic structure, there is a atoms. Number of atoms are there is corner atoms are fixed. The whole corner atoms, there is a one single big atom is combined. That is the whole body center cubic. So this kind of structure, this kind of unit cell is called as body-centered cubic. Uh, this one is having a packing efficiency of 68 percentage. You can see like this corner atoms, all corner atoms, that is top four and bottom four, and the whole body center one atom. So this is the 3D structure like, and like this number of cluster of atoms. If you talk about a face-centered cubic structure, it has the same top four and bottom four. Then along with each faces, top face, bottom face, left, right, front, and back. So these four face center one atom is occupied. You can see a tree diagram here also. So this is the arrangement for face-centered cubic. This has a packing efficiency of 74 percentage. When compared to body-centered cubic 68 percentage, this FCC structure has more than 74 percentage. When you talk about a hexagonal closed package structure, hexagon since the word hexagon, top six atoms, bottom six atoms, that is corners, and the top center, bottom center, you can see one atom. This is the hexagonal closed package structure, and followed by center atoms, three atoms. This is the atomic structure arrangement. So this also has a packing efficiency of 74 percentage. Okay, now I come back to the polling curve of pure ion. Why I am showing this body centered, face centered, and external closed packages? This body centered, this face centered has some property changes. This is needed for our case. Now you see here, on cooling, that is when 15-13 degrees Celsius melted below, then delta Ferrate formation is stopped. That is one kind of a reaction. I said no, the topic, three important reactions occurring. So the first reaction formed is delta Ferrate formation. So this is called as a ferritic reaction. This has body-centered cubic structure. Now, okay, now we are just further decreasing temperature, okay, and below. Now what will happen is, at that way, say 1395 degrees Celsius. So 1395 degrees Celsius, what will happen is, um, the atoms makes some changes. Del ferrite changes into gamma. Gamma means austenite. Here, three terms are there. You have to remember about it. Like del means delta ferrite. Ferrite is the word used in iron carbon diagram. And next is austenite, gamma. This formation will be start forming at 1395 degrees Celsius. So this now we can see body centered cubic is changed to face centered cubic when temperature decreased from 1539 to 1395 degrees Celsius. Now 1395 and below, we can see completely face centered cubic structure. So now what will happen here? The packing efficiency is only 68 percentage because of body centered cubic, and here face centered cubic, so it has a 74 percentage. Then now we can see further decreasing temperature 9 to 12 degrees Celsius. Another changes we have got, that is again face centered cubic, it changes into body centered cubic structure. So this is what we are going to see in depth here. Um, yes, you can see this. crystal structure of ion. This is systematic diagram. Now the same thing I have said, this is the melting point where 1530 degrees Celsius or above is completely liquid. You can see this part, it is liquid. And when you are decreasing further, that is dropping a temperature further, then there is a one new phase form that is delpharite. Now you can able to understand some, I think, delpharite. So this has a body-centered cubic structure. Now, when you are decreasing still further below and below, at 1395 degrees Celsius, delta ferrite is no more existing and it further decreased. Now we can see completely a austenite phase. Austenite, the word is gamma. We will call it as in the chemical term. So austenite formation may form it. This is phase-centered cubic structure. Now this will be existing till 1395 to 912. When it starts 912 and below it goes, then automatically it changes from austenite to alpha. Alpha means ferrite. So again repeating, del means delta ferrite, gamma means austenite, and alpha means ferrite. The word is ferrite. Now this ferrite formation, we can see some metals are non-magnetic, some metals may be a magnetic. So alpha, that means it is a non-magnetic in particular temperature range, say 770 to 912. We want a magnetic material, we don't want non-magnetic material means, then we have to decrease the temperature bit below 770. Until the end of room temperature, we can see completely a ferrite structure. So this is the cooling curve of pure ion. So liquid decreases at 1539. Now you can see formation of delta ion. When further decreases at 1395 to 912, we can see gamma phase. Gamma phase means austenite ion. Then further decreases 912 to 770, alpha ferrite formation will come. This is non-magnetic body center cubic, and further decreases to 770 and below, we can see a magnetic. So this is the cooling curve of pure ion. This is the important thing. That's why I just described this one. So this is basically carried out with a drawing x-axis of time, with respect to time, with respect to temperature. Right. Now the same thing, I'm going to give a brief about these phases. What is ferrite? What is austenite? What is delta ferrite? What is cementite? What is pearlite? What is limellite? These are the common elements will be described in this. Um, I hope you got about this idea, cooling structure of ion. If you have any doubt in this, I want to give one more example with this. If you have any confusion, say if we talk about 1395 to 921, this is assume this is a particular place, say any state. Okay, when we are traveling in India from say like from Punjab to Maharashtra or Punjab to Madhya Pradesh. Now what will happen? That will have different states. So here Punjab means below what will have, then further what will have, that things you know it. So now what will happen? At the state there is a checkpoint, a check post, there other state entry will be permitting it. Now again it is changing it. That means now completely the border crossed from Punjab area and crossed to below than that. That is the way here delta ferrite will be formed only with this range. After this cross that you no more you can able to see a delta ferrite. That is what the simple example I want to say it. Okay. Just small example, that's it. So we'll see first one ferrite. Ferrite is alpha solid solution. That is a symbol used is alpha. That's why alpha solid solution. It is a interstitial solid solution. Do you know the meaning of interstitial? Interstitial means a number of atoms are clustered together in a normal atomic structure. Um, you know about the atomic radius in terms of angstrom. 1 angstrom is the minimum amount. Less than 1 angstrom level, if any other metals are there, then that is called as interstitial solid solution. So a carbon is coming under interstitial solid solution. That is the word they are given this word. Now, ferrite is basically, that is delta ferrite is, ferrite is a body-centered cubic structure. So body-centered cubic means it is a soft material. It is not a hard material. And it is almost a pure ion because the carbon content is very, very less. Okay. I will show the iron carbon diagram. Then I will come back to this word. Right. All of you can view a clear picture about this diagram and please try to go through this. Um, how you should study this iron carbon diagram. To be fact, this iron carbon diagram we can able to cover a complete ferrosilicides, steels, cast ions, everything we can describe with this single diagram. So that is why this is the heart of the heat treatment industry. So how you should read this diagram means you should not go from bottom to upwards. You should go from top to bottom. That means first you should draw this x-axis and y-axis, and x-axis we have to mention it as percentage carbon content, and y-axis representing it as temperature. So temperature in y-axis, x-axis as weight percentage carbon. Now we have already said iron is having a melting point of 1539 degrees Celsius. So 1539 above, it's a completely liquid now. Okay, now we are in this stage. So what will happen is when we are decreasing a temperature, that means we are keeping a material in a furnace. We are setting the temperature of say 1600 degrees Celsius. After some sufficient time, say 2 hours or 3 hours or 4 hours, we have to stop the furnace. Then let it cool slowly, steadily, gradually in the furnace itself. Then what will happen is the temperature measurement we can able to see slowly decreasing. So important temperatures they are mentioned here is this one. Now 1539 we have stopped it. Now at this temperature range, one small reaction is taking place. That is at 1493 or 1495 degrees Celsius, there is a formation of delta ferrite. See, you can see the arrow mark. This is the pure delta ferrite formation. Now this one delta ferrite, what happens is the percentage carbon content, if you want to know, just are you able to see this point, right? Directly, if you're bringing a line, vertical line downwards, you can see the percentage carbon, how much percentage carbon is there here. That indicates a very, very minor, say 0.15 percentage carbon. So only 0.15 percentage. That's why this is called as pure ion. Now I will show that one. Ferrite. Ferrite is a alpha solid solution, body centered cubic structure. So pure ion. Carbon is very less, so it's a pure ion. So the solubility, how much carbon content is there at room temperature, that things is I mentioned it. I will show one more thing. Here, this is the delta ferrite, and this is the austenite gamma, and below is the alpha ferrite. So delta ferrite body centered cubic structure BCC. When we are decreasing temperature 1495 and below, you can see a major portion of austenite, gamma austenite. When we are decreasing temperature or when we are touching a temperature of say 912, slowly austenite phases are removed bit, and there is a combination of both austenite, gamma plus ferrite, alpha. Then further decreasing to say 727 degrees Celsius at below, you can see the entire alpha ferrite. So delta ferrite, austenite, then here austenite plus delta ferrite, sorry, alpha ferrite, and here complete ferrite. So this is the variation. Now I will be saying those temperatures here, how the combinations is. Let's see example. You can able to see the green color line. This green color line, suppose at this particular point, what kind of a composition or what kind of a phase is existing. If you want to know, you can just focus. Here you can see gamma, gamma, gamma. This is a structure, microstructure. This is a grains, different grains. So austenite phase is completely stable. That is what it shows because you can see here fully austenite. Now, if I want to know what kind of phase is there in this particular point. So if we are representing there, you can see austenite is stable, but also small circles are there. Those circles are called as cementite, Fe3C. That is ion combined with carbon, it may form as a carbide. So that is a chemical representation is called as cementite. So the small circle is a cemented particles, little bit is stable. And if you are seeing about this point, you can see complete one structure that is ferrite or pear-like structure. So this diagram you have to draw with your again and again and try to do practice. Then you can able to understand what it is, how it is. First time if you are seeing the sign diagram, if anyone else, then it may leads to some confusions, some difficulties. But actually, this is a really very easy, such a easy process. Nothing to bother about. Easy, just slowly, step by step, from top to bottom, we have to go through it. Okay, so in this x-axis, you can see steels and cast irons. So steel maximum percentage is 2%. Now here, this range is completely for steel category. And when it crossed more than 2 to 6.67%, that is coming under cast iron content. Okay, Larry, I want to ask one question, but I don't know how can I able to get the answer from you. But at least you can listen it. Um, if I ask a general question, steel is hard material or a cast iron is a hard material, what will be the student's answer is? I know 50-50 ratio or 60-40 ratios. 60% people will say steel is the harder or cast iron is the harder. Balance will say steel or cast iron. So 100% answer can't be able to expect it. This is, of course, is obviously nature, but you have to remember why steel is harder, why cast iron is harder. So when carbon is keep on increasing continuously, automatically the hardness is increasing. When carbon content is keep on decreasing, then metal is having a soft material. So if I am pointing this particular point, particular percentage, it's a very less, say point something percentage carbon. It is very soft material because iron is a much soft material. When you have to add carbon, it is getting softness. So 0.2, 0.5, 0.8, 1, 1.5, 2. Now, when I'm comparing this as well as when I'm comparing with this, we can see the material. This is soft material, this is hard material. This is what the way of representing the study of iron carbon diagram. Right? Okay. So our case of this iron carbon diagram, you have to remember the four important temperatures. One is 1539 degrees Celsius, and another one is 1495 degrees Celsius. Then another one is 1147 degrees Celsius, and the last one is 727 degrees Celsius. So these are the temperatures you have to remember. So I will show, or I will just first of all say the phases because I'm completely focusing about the gamma phase or delta phase or alpha phase. You have to remember, no? That is why I already said before. So maximum solubility of carbon in ferrite means it will be ranging from 0.008 to 0.025 percentage. That is almost less than 0.1 percentage. So this is the ferrite category. So due to less carbon, ferrite is a soft material. Soft metal means automatically it has a ductile and low in strength, relatively very low in strength. If we talk about austenite phase, austenite is represented as gamma, as I already said to you. So FCC structure, maximum carbon in ion is 2% maximum. And at this temperature, it is forming austenite maximum. So this is soft, ductile, malleable, and non-magnetic. So if you want to do forging operation or rolling operations, then this temperature is maintained 1000 degrees Celsius. When we are further decreasing, austenite will be formed. Delta ferrite, this is a very starting point. I said no, that is delta ferrite at 495 degrees Celsius. Zero point 0.1 to 0.15 percentage is harder. That is the concept in delta ferrite. So one more phases are the perlite, cementite, ladybirite. These are some names called as from this example. See, ferrite, cementite. That is alpha and cemented Fe3C combined means then that is called as perlite. And iron and carbon with more 0.6 with the 6.61% carbon means then that is very hard and very brittle. That is cementite. And leadiborite means 4.3 percentage carbon adding means then that arsenite, cementite both are mixed. So that is called as leadiborite. These are some terms using. Alright. So reactions talk about three reactions. I said no. This is peritectic reaction. The first reaction starts here, 1539 to 1395 degrees Celsius. So this is called as peritectic reaction. Then second reaction is this one. This is called as eutectic reaction. So eutectic reaction, the major percentage carbon is added there. And the last one is eutectic reaction, sorry, eutectoid reaction. So peritectic, eutectic, as well as eutectoid reaction. These are the names representing it. So there are point percentage. I think you are now clear. Now I will just say shortly about these. Here, delta, pure delta. At this range, this curve above is completely liquid. So liquid below, here liquid, adjacent side left side is a delta. So liquid plus delta will be that. So that is what formation, how to study means. This is the way you have to represent it. So at 1495 degrees Celsius, with the maximum percentage of 0.18 percentage carbon, the liquid is changes into delta ferrite and austenite. Likewise, we have to study. Then next eutectic reaction means 4.3 percentage carbon. These reaction taking place. So here above 0.3, 4.3, here above this point above is liquid. Below we can see austenite plus cementite because adjacent is austenite and right side major percentage carbon is there. So cementite. So gamma plus Fe3C. And if you talk about this electrolyte reaction, this point above is gamma austenite and below is alpha plus Fe3C. So that is ferrite. So this is the ion carbon diagram. Now I want to discuss with you with the important points, critical points. So A1 represents as lower critical temperature, A2 represents as accurate temperature, and A3 represents as upper critical temperature, and A cementite, PM means cementite, is upper critical temperature. Then A4, these are the indications. So temperatures are this. A1 means 723 degrees Celsius, A2 768. So then A3 723 to 912. Then A700 means 723 to 114. Last A4 means 1395 to 1495. You can see here, see A2, A3, A7 A1, and A4. So these is the important critical points. Now I will just give one small information. Um, as I said very starting, when we want to change the property of material, say I want to increase the hardness or I want to decrease the hardness. I have a hard material. I want a soft material. What should I want to do it? Then in such a case, simple. The hard material means this gamma portion is hard when compared to ferrite. So we have to set this temperature range. Say the metal is heated above to 912 degrees Celsius and then holding it for a long time, then cooling in a furnace. So this A3, A2 will comes in. You can see the changes. 723 means pale light begins to transform. The exam 68 means what changes are that? That is what indicated in this case. Completion of ferrite to arsenate maximum. Here, cemented to arsenate changes. That is what mentioned here. So this is what important reactions and our system: peritectic, eutectic, eutectoid. Now I will show separate reactions. Peritectic reaction. I will show this one peritectic reaction. I already said to you. So this one separately I have shown here. See, we have zoomed it. Okay. So this peritectic reaction, what will happen is point. See, this one is 0.18 percentage carbon. At this point, delta solid solution, and that is above is liquid. So below liquid is there, and adjacent is delta. So delta is added here. So liquid plus delta. Now below here is austenite. So this one is austenite. So you can see here liquid, that is this point is the periodic point. P is called as P stands for periodic. So P, that is this periodic point above, you can see liquid plus delta because here liquid, here delta. So liquid plus delta. When heating the material, that is this arrow mark indicates towards left side is heating, towards right side is cooling. So when you are heating and we are decreasing or cooling the temperature, liquid plus delta is changed entirely to austenite. So this austenite is formed. Now you can see this at this point above is delta ferrite or liquid phase, but below you can see complete austenite. That is what is shown here, and that's also similar diagram which I hope it's clear. This is the petroleum reaction. Now, eutectic reaction. Eutectic reaction starts from here. This one. This is the eutectic reaction. You can see the eutectic reaction. See here you can see it. No? The point eutectic E above is liquid, and the adjacent is above liquid plus adjacent gamma, liquid plus gamma. Here cemented 6.61 percentage, so L plus Fe3C, we will call it as. Then this point below gamma plus Fe3C, because liquid is initial stage. When we are decreasing gradually, liquid is disappeared and makes in the form of a solid state. So here arsenite plus cementite combinations is there. So this is the reaction. So at this eutectic point, at 1146 or 1147 degrees Celsius, when temperature is heated above, it will be a liquid. Then when it decreases to this temperature and below than that, then liquid is transformed or changed into gamma arsenite plus Fe3C means cementite. So that is what here mentioned, gamma plus Fe3C. Last one, reductide reaction. Reductide reaction here at 0.8 percentage carbon, the reaction takes place. Arsenite above, below is ferrite. That's one thing. So at this temperature, 720 degrees Celsius, this is existing metal. So arsenite at this temperature, 720 degrees Celsius, above is arsenite. When you are cooled, when you are decreased temperature down, then changed into alpha plus Fe3C, ferrite plus cementite. So this is the reactions you can able to see entirely in this iron carbon diagram, right? So remember eutectic, peritectic, peritectic, eutectic, and eutectoid. And I can show one more thing also. Here, if we talk about a eutectoid reaction, at this line, you can see very clearly this ratio. You can see this is austenite gamma phase. So you can see completely gamma, gamma, gamma. Then when we are in this small curve region, you can see mixture of gamma plus below alpha ferrite, gamma plus ferrite. You can see here, see gamma, here gamma, gamma. At the same time, there is a small formation of ferrite takes place, alpha takes place. So it is start growing slowly. Now, still below near to the line of a A1 line, you can see the gamma and the ferrite small circle is increased to a bigger one. Then the last once line below if it talks, then entirely it is changed into a pear-like. Pear-like means ferrite and pear-like mixing is order. So this is the complete reactions take place. Detective, detective, detective reactions. So have you guys able to understand this question? Sorry, this topic. Because this diagram is very simple. And cover diagram means what and its phases you have to represent it. Some chemical terms are there that you have to remember, ferrite, cementite, arsenite. That's it. And my humble request is this diagram is the most basic for engineering materials. So all of you, whenever you have free time, draw a x-axis, y-axis, and the corresponding income diagram, and the practice, automatically you'll be very strong in this. So that's what it is. Thank you. Uh, I want to know about your things, but I don't know how to. Okay. Oh, I can see chat, but I didn't see any chat information. So my topic is over. And if you have any doubts, you can ask me. You guys will understand. I don't know. If anyone have doubt, you can please ask me. I will explain.